Ever wondered how planets moved? Well, first we'll have to take a look at circular motion. In Newtonian physics, uniform circular motion is when an object travels at a constant speed along a circular path. You can try this by getting a keychain or any other small object and a piece of string and a wide open space so that you don't hit anyone. Then swing it around your finger horizontally to the ground. The velocity of the keychain is perpendicular to the radius of the circle, which is actually along the tangent to the circle at the point. When you release it, you'll see that it flies along the tangent to the circle. This is because of Newton's first law. An object will remain in a state of motion unless acted on by a net external force, which means that something moving in a straight line is going to continue moving in a straight line unless a force turns it. And that's why when you let go of the string, the keychain flies along the tangent of the circle, which was the direction it was moving in last. And in fact, the direction of the acceleration is towards the center of the circle in the same direction as it changes in velocity. So to calculate this acceleration, we can look at one point on the circle, which we can call A. At point A, the object has a velocity of VA. After a split second, the object would have moved to point B and now has a new velocity of VB. Shift the vector VB to meet the vector VA such that we can calculate the difference in the two vectors. Note that the angle that the two vectors make is equal to the angle that the two radii make. Here we can draw an arrow to represent the difference between VA and VB. Since the magnitudes of VA and VB are the same, we can draw a circle using VA and VB as the radii. Now let's backtrack a bit. VA and VB equal to R omega. Omega is the angular velocity, delta theta over delta t. Linear velocity is equal to the radius times angular velocity. Which can be rewritten as R delta theta over t, and you can think of R delta theta as the arc length. Similarly, we can calculate VA minus VB by thinking of it as the arc length of the small circle and get R omega delta theta. Also knowing that delta theta is equal to omega delta t, we can sub that in and get R omega square delta. Acceleration is the difference in velocities over time. Using our previous result, we know that acceleration is equal to R omega square delta t over delta t when delta t approaches 0, which can be simplified to R omega square. Now, we know that centripetal acceleration is R omega square, F equals to ma, a equals to R omega square, so centripetal force is mr omega square. Introducing Johannes Kepler's third law. Kepler's third law states that the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. This can be rewritten as r cubed over t squared. Remember that we previously proved that F equals to mr omega square? By definition, omega is 2 pi over t. Combining those equations, we get that F equals to 4 pi square mr over t square, which can be rewritten like this with 4 pi square k as a constant. Hence proving that F is directly proportional to m over r squared. By Newton's third law, for every action there's an equal and opposite reaction. Hence, F is also directly proportional to the mass of the other planet, denoted by big M. And so that is how we get the law of universal gravitation, which states that every particle attracts every other particle in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers.
And now, my nerdy friends, we can finally enjoy the night sky, knowing how the planets move.